Today's talk is about near-inertial wave energy propagation out of the mixed layer, the role of the submesoscale from idealized process.
Mesoscale.
Sorry?
The mesoscale.
You just said submesoscale, I'm sorry. So the role of mesoscale from idealized process studies to more realistic scenarios. So,
okay.
Pascale, the floor is yours.
Well, here I've listed, in addition to the title, all of my collaborators. So this is a very collaborative effort. So with Mariona, who just recently joined our institute, Northwest Research Associates in Seattle, Washington. Craig Winters, who's at actually Scripps and also UC San Diego. Jeffrey Early, another one of my colleagues, who developed one of the models, diagnostic models that we use. And two French researchers, Pascale Bourret-Auberteau and Yanis Kuipers, who are in Paris, who have provided all kinds of, I guess, suggestions and suggestions for problems to do. They're both observationalists. And Yann Urmière, finally, who supplied us with an amazing data set, which I'll talk about. So the physical motivation for this talk is that, well, it's kind of a very generic motivation. What's the fate of wind-driven near-inertial energy in the ocean? And of course, we'd like to know what fraction actually leaves the mixed layer and propagates into the deep ocean as propagating inertia gravity waves, which often in this talk will be referred to as IGWs like this. And we'd also like to focus on the impact of the mesoscale circulation on this downward propagation. More immediate goals are, as a numerical modeler, can we incorporate a realistic mesoscale to study its role in propagating near-inertial energy out of the mixed layer? And also, can we identify the dynamical mechanisms through the role of these triad interactions? A long-term goal, I would say, very long-term, is to be able to follow this energy that is generated by the wind down to dissipative scales, but that's many years away. So I thought I would start just to get everybody on the same page with just a little review of what I'm talking about. So internal waves in the ocean are primarily forced by wind and tides. Tides interact with topography and generate internal tides. The wind forcing produces these inertial oscillations that have frequency F in the mixed layer. Forcing is just very much restricted to the upper ocean. These inertial oscillations have very large horizontal scales, and on their own, they can't propagate. Okay, so they need some kind of mechanism in order to have shrinking horizontal scales so that they can then propagate downward. So the frequency range for the propagating waves is then greater than F, and it's bounded at the upper end by the buoyancy frequency, N, which is a measure of stratification. So the frequency range is modified when you have ambient vorticity, which here I've just denoted zeta. Okay? And what happens is that in regions of negative vorticity, which we refer to as anticyclonic regions, the effective lower bound that is felt by the propagating waves is decreased. Okay, it's decreased by this amount. And so what happens is that near-inertial oscillations, which otherwise wouldn't be able to propagate downward, now find an environment that is just more conducive. And so they can exist in these regions where F effective is reduced, but they can't really leave. The waves become evanescent. And so basically what happens is that you get near-inertial energy found trapped in these anticyclonic regions. specifically in anticyclonic mesoscale eddies. Mesoscale eddies are features that evolve on much, much longer timescales, or much longer, I shouldn't say much, much longer, than waves, and they have spatial scales on the order of 10 to 100 kilometers. And so you can see that mesoscale eddies actually play an important role in the wave energy propagation out of this mixed layer, and that's the motivation for studying this problem, where you have not only waves, but you have eddies. So how do we study these things? I've kind of spent my entire career right in between here. So I've mostly used Boussinesq models, which are non-hydrostatic models. And these models are really well suited for idealized process studies. You have a single eddy, you have waves. They're really well also just well suited to study turbulence, where you have triply periodic boundary conditions. You don't worry where you are in the ocean. But the advantage of these codes is that they're accurate, because you can, if you have periodicity or if you have very regular boundary conditions, you can use spectral decompositions for all your flows. Spectral decompositions are nice because you can take derivatives as just, derivatives are just a multiplication, and so they're very accurate, and they're also fast. They also rely on very few parametrizations, typically only hyperviscosity, hyperdiffusion, but you don't have the bulk of parametrizations that larger scale models have, okay? But of course, as I said, inclusion of larger scales is limited to very simple features. On the other hand, you have ocean general circulation models, eddy resolving general circulation models. You can actually see the eddies. These models are hydrostatic, and they're best suited for modeling larger scale flows. Okay, you can have open boundaries, you can have bottom topography, you can have coastlines, but you often rely on fairly heavy parametrizations to handle what you can't resolve. Okay? So for example, for near-inertial waves or near-inertial energy, you can resolve that signal near the surface, but because their grid tends to be, the grid of these general circulation models tends to be very fine near the surface and coarse toward the bottom, you can't really resolve, you don't have the resolution resolved to study near-inertial wave propagation out of the mixed layer. Okay? So one of the things that we're trying to do is to solve this. You know, how do we incorporate not only waves, the resolution for waves, but also a wide range of spatial scales into one simulation? So I've split up my talk into two parts. First, I'll talk about a very nice, simple, idealized case that was motivated by some observations in the Eastern Mediterranean. In the Eastern Mediterranean, there sits this eddy. It's called the Cyprus eddy. It sits atop a seamount. It's quasi-stationary, and it's just a nice, simple axisymmetric, mostly axisymmetric eddy to study. And so my colleagues in Paris, Pascale, Roberto, and Yanis Kuipers, had some nice observations at the base of this eddy. They saw a very strong internal wave signal that would just sat there for quite a long time. And so they kind of asked me if I'd be interested in modeling this. And so we did a nice simulation in a Boussinesq model with a single axisymmetric eddy perturbed by a strong wind impulse. So the observations had lots of information on the stratification profile information on the waves, but they didn't have any information about the wind forcing at that time, at least at the high resolutions that we were interested in. And then the second part of the talk will be moving from this simple example to a more realistic mesoscale field forced by ECMWF winds. And I'll show you the results of nested simulations inside a regional data set in the Western Mediterranean. And I wanted to add something about the Mediterranean basin. The Mediterranean is a kind of it's a semi-closed sea, and it exhibits all the features of larger scale circulations. It has an overturning circulation, it has upwelling, it has eddies, but everything's on a reduced spatial scale, which is quite nice. So it's a really nice, ideal laboratory for oceanographers. And as a result, there's lots of observational data. And so for numerical modelers, it's quite nice because we have things to compare to. So that's why these two problems are actually in the Mediterranean. Okay, so first I'll talk about this Cyprus eddy case. I think it's just a really clean and nice example, so I thought I would just talk about it some more. So it's idealized. Okay, so we initialize an axisymmetric eddy in cyclogeostrophic and hydrostatic equilibrium. And so without any kind of perturbation, this eddy is just going to sit there indefinitely. And we add to it just a wind impulse in the x direction, like this. And this wind impulse is confined to the upper 200 meters. Actually, it's less than that. These arrows are too low. Anyway, like this. So that's the cross-section of the vorticity. And so we matched the scale of the eddy and the stratification to the data. And so in blue is just the mean stratification away from the eddy, and in red dashed is the reduced stratification inside the eddy. Okay? So nice, simple expression. That's the eddy, and that's the wind impulse. Yeah. It's a stable eddy by itself without. It'll evolve. No, it's on an F plane, so it'll just sit there.
Okay.
It's in cyclogeostrophic and hydrostatic balance.
Could split up, right? If the Rossby radius is too small or too large, and it splits up into two after a couple of months.
This one did not.
Okay.
We ran it without any kind of forcing, and it just sits there for months.
What about the energy level of the waves you put in and the eddy? Are they comparable?
So let's see, I can't remember now. They are comparable. So I do remember the impulse was on the order of 20 centimeters per second, and the eddy was, comparable, I would say. Yeah, that actually matters. So we were just matching observations here. So, and so to identify what is a wave and what is the eddy, we did a simple decomposition where we first defined from the full velocity field, and actually I'm just doing this for the velocity field, but we did this for all variables. So you average over an inertial period, say, okay. So you average your full velocity, full dynamical variable over an inertial period. And then you define a fast component as the difference between your full field minus the slowly evolving field. you go further, recognizing that inertial oscillations have no specific horizontal scale. I mean, the scale in the numerical simulation for the inertial oscillations is set by the size of the domain, okay? So now let's just define the inertial oscillation variables to be the area, the fast component averaged over the area of our domain. And we'll take the wave component, the propagating wave component, to be the difference between the fast component and the inertial oscillation part, okay? And so just to show you, so here's a cross section. These are XZ cross sections. On top here is the eddy, okay? Here you'll see the inertial oscillations, and so you can see that they're confined to the surface. And here is the wave field, which at time t equals 0 is non-existent. Okay. Why doesn't my movie play? Okay. So you can see that the vortex remains for, oops. Oh, the movie. Let's see. Maybe I'll just do this slower. I'll just do this. Is that working? Yeah, okay. So you can see the inertial oscillations just changing sign. This is, I think I'm plotting U. Yeah, I'm plotting U here. So one of the components of velocity. And so in time, and I'm moving in time, you can see the appearance of an inertial gravity wave signal propagating downward. The energy is propagating downward. The eddy really doesn't move much. And the inertial oscillations just go back and forth because in time. And so, yeah, okay, good. It's playing here, but it's not playing there. Okay. I'll just wait for it. So you see that by and large, the waves have a horizontal spatial scale that kind of matches the spatial scale of the eddy. And the only time scale really, and the waves actually have the same time scale, roughly, as the inertial oscillations. So you can say, well, the wave time scale is set by the inertial oscillations, and its horizontal spatial scale is set by the vortex. So we wanted to understand what the mechanism was for this. Oh, well, first, yeah. So first, so with that decomposition, that mixed or hybrid time and spatial decomposition, we were able to show, so here is the change in energy, in energies, okay? So you can see that the near-inertial oscillations lose energy toward the surface. The waves gain energy at the surface, and there is also, at the base of the eddy, accumulation of wave energy. The slow vortex flow, on the other hand, really doesn't change appreciably. And if you plot this as a function of time, here is the total energy. So there is a little bit of dissipation, but really not very much in this problem. You can see that the vortex energy is here. So actually, in answer to your question, Jim, the inertial oscillations have more energy than the the geostrophic flow. And so really the only energy exchange is between these two.
So the left plot, what time is that at?
Oh, what?
What time is that at?
This is at the end of the simulation. Yeah. So in this case, waves draw their energy entirely from inertial oscillations. And again, the time scale is given by the inertial oscillations. And there's just a catalytic effect. So this was done with this oops. Why do I have that? Oh, okay. So what we were trying to also figure out was what the dynamical mechanism was for this. And so we formulated a wave equation from the nonlinear Navier-Boussinesq equations. And on the right-hand side, we have all of the nonlinear terms. Okay. Actually, I shouldn't say not, in this case, not all of the nonlinear terms, only the highest order nonlinear terms. Okay. And so you can actually exclude most of these terms. And so the only one that is capable of forcing waves, because you have to have waves at the inertial frequency, and with the correct scales, is this term right here, which you can also rewrite as the vertical gradient of the advection of vertical vorticity by inertial oscillations. We can go further in understanding what's happening with Jeffrey Early, one of my colleagues, with his generalized wave vortex decomposition. He decomposes all flow variables into these three components: inertial oscillations, gravity waves, and geostrophic flow. And he formulates an energetically orthogonal decomposition. Okay? And so looking at the nonlinear terms with his decomposition, here's a plot of the rate of change of the wave energy and the rate of and the flux due to the interaction of these three terms. And it's just perfect. And here's the loss of inertial energy and that triad again. So it's just a beautiful little example. Unfortunately, the real world is not that simple. And so, in the second part of this talk, what I'd like to explore is, so I was in Paris and we were finishing up this paper on the Cyprus eddy, and Pascale and Yanis just happened to have talked to Yann Urmière, who's in Toulon, who had this amazing data set that he had produced. But in Toulon, they really exploited the large-scale aspects of the problem, but nobody had really looked at the smaller scale stuff. And so this is a NEMO. So NEMO is the European general circulation model. For the Gulf of Lyon, here's France, and here is Spain. So it's right in here. So the features of this data set are that it has essentially 1 kilometer resolution. So it resolves the submesoscale. It's got 130 vertical levels with meter resolution at the top and 30 meter toward the bottom. It has 2 years of hourly output, which is kind of amazing. Finite difference. It's a hydrostatic code, solves the primitive equations. It relies on subgrid scale parametrizations, and it's forced with hourly atmospheric fields. So of course you're going to have near-inertial wave excitation. And so at about that time, Mariona and I were talking, and we were trying to figure out how we could extend the Cyprus eddy problem. And so we were just thinking, okay, well, we could look inside this data set and find a couple of features that won't be axisymmetric, and what could we do with it? and I happened to call Craig Winters to talk about something completely different. And I said to him, oh, by the way, you know, Mariona and I are writing this proposal, and we're going to do this. And he says, oh, well, I have just the tool for you. Craig was developing this generalized Boussinesque model that could handle arbitrary boundary conditions. So he said, why don't you nest a Boussinesque model inside this data set, and then you'll have everything that you need. And so we decided to do that. And so we were writing this NSF proposal, and we had 1 week left before we had to submit it. And Craig gave us this idea, and we rewrote the entire proposal, and it got funded. So, you know, never give up. Anyway, so we first applied like an eddy following algorithms to see what kinds of eddies there were. And then we just picked a little region, and we nested the Boussinesque model here. So one of the really nice things about Craig's code is that you don't have to resolve the entire water column. So you can be above the topography, for example. We don't want topography in this model. Okay, so we've done several simulations in different regions. So the first one we did was around here. Then we moved south into a deep convection region. And most recently in October, we went to Paris, Craig, Mariona, and I, and set up a simulation like this in the Strait of Sicily. So we're kind of in the Mediterranean, but moving around. Okay. So, yeah, and one thing to say is that the NEMO model uses a free surface. FlowSolve, the Boussinesque model, has a rigid lid. And so what we do is that we impose horizontal pressure gradients to match what the free surface is doing at the top. So how is this all possible? Okay, this is Craig Winters' work that I'm presenting. And so he happened to be reading in an obscure mathematics journal from Bulgaria something about the power of these Bernoulli polynomials. And so what he does is to expand all variables in the flow, so velocities, densities, into a sum of three series, okay? And so he does this over a domain of 0 to 2L, so it's 0 to 2L. And these u sub n's here are related to the Bernoulli polynomials through this expression here. And Bernoulli polynomials have very nice recursion formulas. And so they're easily computed. And this q here can be taken to be a very small number. It has to be odd, but it can be 7 or 9. Okay, so and you exclude all the even polynomials because of symmetry. Okay, and so and 1 you can exclude as well, and I can't remember why. So you 3, 5, 7, 9. So you can have 4 Bernoulli polynomials. And so one set of them handles what happens at one end and the other set at the other end. And so what you do is that you pick these coefficients in such a way, actually you pick these functions in such a way that at one end of your domain, the Bernoulli expansion matches the value at the boundary. And at the other end, this particular set here, has a vanishing derivative. This expansion here has the opposite effect. So it matches the value of the function at the boundary, and it has a vanishing derivative here at the other end. And so now you can define the remaining part of your expansion to be the difference between these two. And so, you don't have any problems at the boundaries. Those have been taken care of by the Bernoulli polynomial pieces. It's differentiable, it doesn't have any singularities, and therefore it can be expanded, this f sub q, in cosine series. It's a really clever technique. I'm kind of amazed, actually, at how clever it is. So another aspect of this problem is, and just as a reminder, if you have simple boundary conditions, then solving for the pressure is not a problem. So if you have a pseudo-spectral code with periodic boundary conditions, you don't even worry about the pressure. The pressure solves, you can solve the pressure through a division by the wave number. Okay. For finite difference codes, it's typically more involved, and it's a two-step pressure projection method, which involves the first step where you solve the equations of motion, you exclude the pressure gradient term, and then you correct that solution by imposing continuity. Okay? But with arbitrary boundary conditions, the pressure projection method also involves just a little bit more work, because you need to have the inner and the outer contributions taken care of. And so what Craig does is that he rewrites the pressure as the sum of two terms. One term, phi, is assumed to be unknown. Psi is assumed to be known. Phi satisfies the Poisson equation with a homogeneous Neumann condition on the boundary. And phi is unique up to a constant, and we choose that constant to be 0. And psi is not unique, and Craig solves actually a diffusion equation to solve it. So basically what you want is a psi that is sufficiently smooth throughout the domain. So phi handles things on the boundary, and psi handles things inside the boundary. Okay, so that's enough for the method, but we have a publication on this, which
Bernoulli polynomials have spectral accuracy and exponential convergence.
the whole method has near spectral accuracy, I would say, not complete spectral accuracy, but it's computationally very efficient. So, So the nesting strategy that we've used is this. So we start with an initial condition, which is basically a 3D snapshot of one of the solutions from the general circulation model. We interpolate it onto a finer regular grid. And the boundary data, we basically take the Glazur 64, that's the name of the simulation, of the NEMO simulation. And so we have that data at every hour. We interpolate it onto our time steps. And so between 2 hourly saves, we just interpolate linearly to get the boundary data at every time step. And then we do, we adjust the time step, we adjust the dissipation to ensure stability. And we need to do some smoothing at the boundaries to ensure stability, because, I'd like to say this is actually quite non-trivial when you think about it, because, non-trivial because you've got the outer data set solving non-hydrostatic primitive equations and the inner nested solution satisfying a different set of equations, okay? So it took us about 3 years to be happy with simulations. So yeah, I think I'm going to run out of time. I don't want to do that. So here's a comparison. So here is our nested domain, and we have 3 synthetic moorings, vertical moorings here. This is the bathymetry streamlines. That shows just the general circulation in this area, bathymetry. The density anomaly and the vorticity fields show the emergence of filaments and density fronts and all kinds of features, finer scale features. And so this is after 7 days at a depth of somewhere in the mixed layer. Okay, so pretty good agreement. We can't run it indefinitely. We can run it for about a month until the solutions diverge too much, right? Because you've got the inner solution just evolving completely differently at some point from the, well, and so you're trying to relax this inner solution to the outer solution, and if the mismatch is too great, it doesn't work anymore. But to show you, so what the wave signal looks like, in the OGCM, you see the presence of inertial oscillations at the top, but the wave signal, if you can call it a wave signal, is really dominated by mode 1. Okay? And you can see that in the velocity and, structure. Here, right here, is an indication of where our flow solve bottom boundary is. So we don't go all the way down to the bottom. We don't need to. And just to show you, you get a much richer wave signal and downward propagation in the nested simulation. Okay. Upward phase lines, downward energy propagation. And so here's a comparison of the OGCM and the flow solve. So much more structure in the flow solve. And you can see that here too. Yeah. Okay. And so we can look at frequency spectra. And so here are some observations in black. Here is the nested simulation, and in dashed lines is the general circulation model, the Glaser 64. So you can see that there's good match at frequencies less than f, so that's outside of the inertial of the wave band. But above f, we have much more. We have 2 orders of magnitude higher in wave energy. And we replicate the energy levels up to 3f in the observations. So I think I'm not going to have time to really do justice to Jeffrey's model. Let's just say it's a great model, and you can use it. So you're given an arbitrary vertical stratification profile. This model can evolve wave and geostrophic components separately in time. Okay? And the model can be used as well diagnostically, which is what I've done, to identify wave and geostrophic components. Okay? And so any dynamical quantity, you can define any of them, can be projected onto these basis vectors. And the nice thing about this, oops, that arrow should have come down. About this basis, I mean, bases are not unique, but this one is very nice. It's energetically orthogonal. It's also entstrophically orthogonal, and it preserves QG, PV, and mass very nicely. And so what can we do with this? Well, am I going to have to quit in 4 minutes, or can I? We can go, okay, okay, good. Good. Yeah. So the one constraint with the model is that you have to have horizontal periodic boundary conditions. Now, I do not have that. On the other hand, I can always taper, so I save my output, I taper in the horizontal to do the analysis. And so I taper the dynamical fields to obtain horizontally periodic representations. And then I use this wave model to project solutions onto the spaces at every safe time step. And then I just compute whatever I want. So what am I interested in? Well, one thing I can do is to look at the distribution, the spatial distribution of wave energy as a function of vertical mode and horizontal wave number. Okay, and here in white are the hydrostatic frequencies, hydrostatic frequency isolines. Okay, and I do have a movie, but I think I have to go over here. So you can, so initially all of the energy is confined to the lowest mode and larger scales. And as a function of time, you can see the energy going to smaller scales, higher modes. And this checkered pattern, we believe, the checkered pattern that you see, we believe is just because the modes kind of switch signs. And so as you're getting energy to go to different modes, you get this wave-like pattern. So one of the questions that we were interested in was, are these excited waves non-hydrostatic? Okay, we have a non-hydrostatic code. Are we actually really using it? Well, it turns out that you can see here, wave energy actually spreads along hydrostatic frequency lines. So we have increased vertical resolution, so it excites waves of smaller horizontal scales, higher vertical modes, but in fact, they look pretty hydrostatic, okay? And a measure of non-hydrostaticity can be computed from Jeffrey's code by looking at the ratio of eigenvalues for hydrostatic and non-hydrostatic waves. So a ratio of 1 means that the waves are hydrostatic, okay? And a ratio greater than 1 means the waves are non-hydrostatic. So you can see that the only place where we would get non-hydrostaticity is here, and we're not in that range yet. Okay? So we have a richer spectrum of waves, but we're still at this point within the hydrostatic regime. It's disappointing, but it's not the end of the story. So, let's see, I was gonna, show you, oops. Yeah, another thing you can do with the model is to look at the nonlinear terms, look at all the nonlinear triads, and try to see where energy is moving, okay? So if we do this, here is the sum of all the energy transfers, and unfortunately, this is mislabeled. So in red is actually the geostrophic flow. In green is definitely the inertial oscillations, and in blue is the wave field. In black is the total nonlinear transfer term. So the sum of all possible nonlinear transfer terms is nicely close to 0, which is what we want. That's just a sanity check. And we see from this that, in fact, the inertial oscillations are always pretty much losing energy, okay? So where's that energy going? So we can look at the different triads. And so just looking at the transfer triads in the inertial oscillation flow, you can see, for example, here, So now what we're looking at is the projection of that nonlinear term onto the geostrophic flow, inertial oscillation flow, and inertial gravity wave flow. Okay, that's what the triads that I'm showing are. Okay. So for example, here, this would be in the inertial oscillation kinetic energy budget, the triads that transfer energy to the gravity waves and also to the geostrophic flow. I don't have time to go over this particular one, because I think I'm not going to talk more about these triads, but if you're interested, I'm happy to discuss them. I'm kind of excited about this application of the wave vortex model. So here we identified a dipole in one of our data sets. Okay? And what I've plotted here are the positions as a function of time of the anticyclone core and the cyclonic core. Okay? So this is a horizontal cross-section of vertical vorticity, normalized by F. Here is now the wave energy, total wave energy, computed from the wave vortex model. And again, so here in black is the position of this horizontal cross-section. And here are the positions of the anticyclone and cyclone. And here is a vertical cross-section of the vertical vorticity. Okay? Here's the mixed layer down here. So I'm going to play it slowly because okay. Is it moving? It's not. Okay. Well, okay. It's going too fast, so. But you can see, okay. This dipole doesn't live forever. But what you can see, if you look at the wave energy plot, is that you see bursts of wave energy in the core of the anticyclone. Oops, yeah. As a function of time. Unfortunately, the eddy then gets destroyed. And yeah, at about here, you see that the maximum and the minimum are now at the boundary and no longer where the thing is. But what I was really happy to see was just this concentration of wave energy in the anticyclonic core, which is what we would expect. Yeah, oops, now it's playing. Okay, anyway, I'll conclude here by saying, okay, well, we've successfully nested a Boussin-esque non-hydrostatic model into this hydrostatic data set with this, oops. I'm getting ahead of myself. Thank you for your attention. So we have enhanced downward propagating waves in this nested simulation. Waves exhibit this richer spectrum, but again, we're not in the non-hydrostatic regime. We've demonstrated the of this wave vortex decomposition. Future directions involve further analyzing the output to compute the vertical energy flux, which we can do very easily. And we'd like to push these simulations to further nesting. And these will be much easier because they'll be flow solve to flow solve, so same equations. And so just to give you an example of what you can do with these nested simulations, this is a single eddy. And so we have 3 levels of simulations. So here's the parent simulation we take the parent simulation and we decrease the region. And here now simulate this and go down further. So parent, child, grandchild. So that's what's next for us.
Yes, thank you very much, Pascale. We have time for 2 to 3 questions.
So you were talking about inertial oscillations, near-inertial waves. So I wonder, when you say IO, those are pure inertial.
Yeah, the community tends to mix up near-inertial oscillations and inertial oscillations. In this case, they mean the same thing. So,
But the same thing, meaning it's not at F, it's nearby F, but
well,
not exactly.
inertial oscillations, technically speaking, are at F. Near-inertial oscillations could be propagating, but people use near-inertial oscillations a lot to mean just.
Okay. So then in the first part of the simulation where you force it,
Yeah.
those are nearby F waves.
Yes, yes. Yeah. Yeah, they are F. I mean, even the waves, the propagating waves don't have frequencies that are much above 4F.
Did you look at the energy, how much of it was in the Bernoulli modes versus I guess the near-inertial stuff was mostly in the cosines, is that right? Or? Well, I mean, you have some energy in the Bernoulli modes and some energy in the sinusoids. Did you do that decomposition?
No.
Yeah.
No.
Okay.
We didn't attempt that at all.
Maybe if no one else has a question, from the first part of your talk, the vortex didn't lose any energy.
Yeah.
But you had a plot of U, I guess, and there was sort of an asymmetry. I mean, it was distorted quite a bit, right?
Towards the end of the simulation, yeah.
But there was no real, I didn't understand why there should be a sign of that. I mean, where does the asymmetry come from? I guess, is it just because of the initial direction of your wind? I mean, it's an F plane, a circular eddy, so why should it distort one way or the other?
Good question. I don't know. Yeah, I mean, the vortex, once it's perturbed, develops this mode. I'd say it's mode 1 axisymmetric, or mode 2 possibly. You know, you get pulsing, and then you get this little precession. So maybe it was just that particular cross section.
Maybe it was just the particular time that you chose for the plot. Yeah. Okay.
Yeah.
Okay, then let's thank Pascale once again.